Everyone, this is the third part for this discussion on 3D and 2D equilibrium and free body diagrams, and we would like to proceed with that. I just want to share with you that little quiz so that we can warm up and understand what is happening. If a support prevents rotation of a body about an axis, then the support exerts what on the body? The word rotation triggers moment. So the answer is A. It's developing a coupled moment reaction. Question number 2. When doing a 3D problem analysis, you have what? So how many equations of equilibrium? Is it 2D or 3D? 3D. That means fx, fy, fz, mx, my, mz equals 0. So the answer is D. You have 6 unknowns. Let's move on to the next part. Applications. Remember the ball and socket support that we're having right here is preventing horizontal, vertical, and the other direction, fx, fy, fz. However, it's allowing rotation because it can rotate, allowing rotation about x, y, and z. That means we are not developing any moment about x and y and z. And this kind of support you'd like also to understand is preventing movement in this direction and vertical, but it's allowing movement in that axis right there. If you have a support right here, so you do have that kind of structure which is supported by a cable, for instance. So you have a certain weight for it and you have a cable, and you are able to identify what reactions you have. I'm just sharing that with you so that to refresh your memory and repeating stuff that we talked about before. In 3D problem, you have one vertical reaction at the surface. Here, the ball and socket, we said we developed 3 support reaction, fx, fy, fz. In this support, you are allowing movement. So you're not developing any force along here. You are preventing in that direction. So that is fx, and you're preventing vertical fz. And also you are developing mx and mz, but allow rotation about the rod itself. That means you're not developing any moment. So again, you have 4 unknowns, as you can see right here. If you have a simple hinge, in this case, you are going to prevent 1, 2, 3 translation fx, fy, fz, but 2 moment, no rotation about this axis, mx, no rotation about this axis, mz, but you allow rotation about the connection of the joint, so you are not developing my. So this is 5 unknowns right here. We just want to highlight that so you can identify that. In the test you will be given some of this. I'm just going to ask you to identify how many unknown reactions you might have. This is a little bit tricky, but if you have a fixed support here in the wall and 3 ends afterwards, once you see that fixed support, that means it has 6 unknowns, fx, fy, fz, mx, my, mz, if that is the case. However, in this case, we are allowing rotation right here, so we don't have my. If it is totally fixed, that means it's 6 unknowns. If it is not fixed, it's allowing rotation, then you are releasing this kind of rotation, releasing the moment, so you don't have more than the 5 unknown reactions right there. If you have multiple points of connection that are properly aligned as bearing and stuff, I will focus more on the fx, fy, and fz. So I will say at that point C and B and A, we are going to develop reaction. For instance, at point A, we are preventing vertical movement. That means we are developing A in direction of Z. We are preventing movement in this direction, that's AY. However, we are allowing movement here, so we are not developing another reaction. So at point A, you have 2 unknowns. How about point B? You also have 2 unknowns. How about point C? You also have 2 unknowns. Let's go to the very right element. You have a table like that. It's supported at a joint right here, a hinge at point C, a roller at point B, and another support here at point A. 2 unknowns have been developed at A, roller support at B, providing 1 unknown reactions, and here we are providing 3 translation. Are these the only ones? We have moments as well, but let's say that we care about the forces more than the moment for now. So these are the kind of support reactions that you're having. What kind of equations of equilibrium? As we said, the 6 equations of equilibrium that you have. So these are very important for us to identify and to properly prevent any kind of failure of a structure. What do I mean by that? We have improper constraints. For instance, something like that. Let's look at the bottom one right here. I can see something here that is not properly constrained. I have 2 unknowns here, 1 unknown here, 3 equations of equilibrium. So it's deceiving, telling us, oh, I have 3 unknowns, we should be fine. No, because in this case, all the reactions meet at one point, and you can easily, for that rod, go up and down, nothing preventing that. So that's unstable. Similarly, for this connection, I have a socket and bolt support here, socket and bolt support here. That is fantastic, but I can draw a line in between, and if I have any unbalanced force P at an offset position between the line AB and the point of application of B, that means the sum of moment is not equal to 0. That means it's unstable. I just wanted to highlight that so that we are familiar with these kinds of problems. Let's see the properly constrained structures. How can we solve them? So in the test, if you have something like that and they ask you, draw a free body diagram, that's the first part, and then write equations of equilibrium and solve it, that's the second part. Let's see. When I see that cable, what do you think? I cut through it. I develop how many unknown? 1 or 2 or 3? Only 1. So I have 1 unknown here. How about here at this location? For this part, I'm preventing AX and AZ. So let's look together what we have. I develop AX, I develop AZ, and I develop moment about X, moment about Z. However, I'm allowing movement here, so I'm not developing any force along here. I am allowing rotation of this rod in this connection, so I'm not developing any moment. So how many unknowns reactions I have here? 4. And here I have 1. So let's see. I have several equations of equilibrium that can help us. So I believe if I do sum of force of X equals 0, you find out that AX is 0. If I do sum of forces in direction of Z equals 0, so I have AZ, I have minus 80, and I have plus FBC. Perfect. So I have this equation, but I have 2 unknowns. That's not going to help me much, right? Let's see. Sum of the moment about Y equals 0. I have nothing here, nothing here. So what is that going to cause moment about Y? So let's say, where is Y? Here is Y. What is causing rotation about Y? None of this, these are support reactions, they're not causing any rotation about Y, but these 2 forces, the blue and the red color forces, are causing rotation about this axis. 80 times 1.5 clockwise gives you negative, and FBC times 3 positive. 1 unknown, so you find FBC, and FBC turns out to be 40. You plug it back into sum of force of Z, you find A sub Z. Done. So you came up with AX, AZ, FBC. Are we done? Not really. We would like to get the moments. How can I get the moments? If you use these equations, that's great. Let's move on to other equations. Moment about X and moment about Z. Sum of moment about X equals 0. I have MAX. That's fantastic. What else? What is causing rotation about this axis? The 80 times that distance, 6, is causing negative moment. And the 40 for FBC, the red color force, times this distance, also counterclockwise, causing moment. From this, you find MAX. Fair enough? And when you do the same thing for some moment about Z, you find out that MZ is 0. These are very good examples. Problems that we're having. Another example here, you have a uniform plate. It has a certain weight at the center, right? 500 pounds, and supported by all these cables. So how many unknowns we have? 1 cable, 2 cables, 3 cables. I have 3 unknowns. So what comes to your mind is the free body diagram. Here we go. 1, 2, 3, a red color free body diagram. And if you go back to the problem, you have 200 pounds here in addition to the own weight. So come back to here we go, the 200 edge force and the 500 pounds applied at the center. What equations can we use? I can simply say sum of force in direction of z equals 0. Oh, fantastic. But I will have three unknowns. TA, TB, and TC minus 200 minus 500 equals 0. Keep this as equation number 1. What other equation? I can simply say sum of the moment about this x. Why can't I say sum of forces in x and sum of force of y? Because there are no forces in x, no forces of y, so it's not going to help me. So let's try sum of moment about x. Does that force cause any moment? Nope. How about this t? Yes, TA times that distance, 3. How about the 200? Yes, 200 times 3. How about the 500? Yes, 500 times 1.5. How about the TAC? Yes, TAC times 3. So you have two unknowns in this equation. We're getting close. What else we have? Sum of moment about y. Same thing, forces times distance. So you end up with this equation. So you do have those three equations in three unknowns, TA, TB, TC, and you can solve them and you can find out the answers as you can see right here. These are very good examples that I want you guys to familiarize yourself with and be able to solve. Another concept, if I give you a rod like that and this supporting using cable, so you do have a cable right here and you have a ball and socket support, so you have a cable right here, and you have a ball and socket support, so you do have how many unknown support reactions you have. What do you think? The ball and socket provides three unknowns, right? MX, MY, AX, AY, AZ. And you have these two unknown reactions in the cable, so the answer is B, 5 forces, as you can see right here from the free body diagram. Fair enough? That is something that I want you guys to familiarize yourself with and be able to solve. Let me show you another problem. If I have a plate that's supported again on ball and socket support, and that is at point A, let's say, and the roller at point B, and another cable right here. How many unknown support reactions? So we have 1, 2, 3, 4 at the bearing, 1 at this tension. So I have 5 unknowns right there. I hope that you are happy with this kind of overview of that topic. And with that, I think you are prepared for equilibrium of 2D and 3D problem, and best of luck. Thank you.